we continue with the other part of the term that we had in the definition of microprocessor, another thing that we have is the arithmetic and logic operations. So, this is the basic thing, like any processor that is designed is supposed to do some operation on the data, and what are the operations that can be done. So, this is decided by the processor design team. So, some processor which is very simple. So, there we may be satisfied by in doing say basic operations like addition, subtraction. Okay. So, some processors may support multiplication. For example, if you look into 8085, it does not support multiplication, but if you go to other processors like 8086 or say even 8051, so those processors, so you will find that multiplication is supported there, division is supported by some of the processors. So, that way what are the operations that we are going to support, so that is decided by the designer of the processor. And if we are supporting more operations, means the circuitry, associated circuitry will become more complex. So, the cost of the system will go up. So, its complexity will increase. So, every microprocessor has arithmetic operations such as add, subtract as part of its instruction set. So, normally addition, subtraction, these are very common. Most microprocessors will have operations like multiply and divide, but it is not always true. Some of the newer ones will have complex operations such as square root. So, you can if you are designing a dedicated processor for some application, so which are known as ASIP design, ASIP. So, if you are having these ASIP designs, which stands for application specific integrated processors. So, for the ASIP design, so we have got special instructions. For example, we can say that we have got one filtering operation, that is you are getting the data samples from the outside world, and for in a signal processing application, so we are doing some filtering and all that. So, there this entire filtering operation may be a single command, in response to which the processor executes the filtering routine, and accordingly the filtering operation is done. So, they will come under this ASIP design, but those are very complex. If we do not go into that, even then this we can have the basic instructions or basic operations by all these microprocessors. So, apart from this arithmetic operations, so there are some logic operations like AND, OR, XOR. Then there are some shifting operations, shift left, shift right, like that. So, shift left, shift right, so these they have got several applications. So, one particular application is many a times we need to multiply a number by 2 or powers of 2. So, if you multiply a number by 2, that means you are actually doing a left shift of the whole thing by 2. So, like say if I have the number say 3, if I have the number say 3, so 3 in binary notation, so it is so 1 1. Now, if you are so it is a 1 1. Now, if you are doing a left shift, then what will happen? So, this bit will become 0. So, these ones are shifted. So, this one is shifted there, the next one is also shifted there, and the new 0 gets introduced at this point. So, you get the new pattern as 1 1 0. So, and if you look into this value, so the binary value of the decimal value of this is 6. So, that you see that it is a it's nothing but multiplication by or multiplication by 2. That way shift left is a multiplication by 2. Similarly, shift right. So, this 6, if you shift right by 1 bit position, you will get back 3. So, that is division by 3. So, we have got shift left and shift right for doing the operation. So, that is one type of application of the shift type of operation. Another application that we can have is many times we need to mask out certain bits from a pattern. So, there also to prepare this mask, this shift instruction will be utilized. So, we will see that later when we go into that type of application. So, the number and types of operations define the microprocessor's instruction set and depends on the specific microprocessor. So, the what are the operations that you can do and on what type of data? Can we, for example, can we have a microprocessor that performs say the string concatenation operation on some string data? So, does it support string type data, and if it supports string type data, can it do string concatenation? So, if I design a microprocessor for that purpose, for doing this string operation, then the string concatenation is definitely one important operation. So, naturally in that case we will be introducing that instruction into the microprocessor basic operation set. So, this basic instruction set. So, the instruction set, like if you are trying to learn about a new microprocessor, you should learn about its instruction set and the data type that it can handle. So, if we are going into the definition further, say the procedures, the produces the data that is produced by the microprocessor. So, they are actually for the user to see the result on the execution of a program, the result must be presented in a human readable form. So, we should be able to understand the value. So, if it is if the value is stored in the memory, then a general user will not be able to see that. As a result, there should be some output device onto which the result should be given. So, that result is given in the normally we have got output device like say LEDs, we can have say some simple printer, or it can be say a some LCD display. So, we can have some type of display onto which the result will be shown. So, that way we can have this results produced by the microprocessor, and the produced result should be readable by the human being. Another important thing that we have not considered is the stored in memory. So, what do we store in memory? So, we have to we have already seen like what is memory. So, we can just quickly recapitulate. So, this is the location from where the information is kept while not in current use. So, what do I mean by not in current use? So, not in current use by the processor. So, processor is at present not using it. So, processor at present is using the data which is inside the processor, inside the microprocessor. So, it may be in some CPU register, or it may be the data or the instruction that has been fetched by the processor from the memory. So, it is in the instruction register, or it may be some internal register, or it may be some operation that it is doing in the ALU. So, ALU temporary registers are holding those values. So, that way, so those are the data that are in use, and at the same time there will be other data which are not in use. So, they will be used in future. So, they are actually stored in the memory, and we know that they can hold number of bytes in it. So, the kilobyte, megabyte, gigabyte, etc. So, they are the different sizes of the memory that we have. So, what do you mean by stored in memory? So, when a program is entered into the computer, it is stored in the memory. So, because you cannot store the program in the processor, because processor has got only a few registers. So, if we use that for storing the program, then where are we going to store the variables and the data part of it? So, what is done is that the program is stored in the memory, and as I said that microprocessor, any microprocessor, when it starts executing, so it is actually getting the instruction, it is getting the instruction from the memory. So, it brings the instruction from memory one at a time. So, first it brings the first instruction, executes it, then it brings the next instruction, executes it, that way it goes on. So, apart from this program, so memory also holds the data. So, in the part of its execution, if the microprocessor finds that it needs to read some data from some memory. So, for example, it may be that the instruction that it is executing is adding the content of two memory locations and storing the result in a third memory location. So, for executing this instruction, the processor will need to get the contents of the two memory locations from where the data should be taken. They are to be added, and finally, the value should be stored in the destination memory location. So, that way it has to have this memory also works as the place where you store the data. So, and finally, so this produces part we have already discussed. So, it is actually showing the result to the user. So, overall diagram, overall picture is like this. So, if this is the microprocessor, so it has got with it some input devices by which the input data can be input program data can be taken, and it is producing some output which is going to the output device. And in this particular diagram, the way it is represented, it is somehow the program has been loaded into the memory. Okay. Though normally we have got some facility by which we can load this memory by some other means, maybe by some separate computer or by burning the EEPROM part of it with the program, whatever. Somehow the program has been loaded into the memory, and this microprocessor, it asks the memory to get the next instruction, it gives the next instruction. So, it starts executing, and in the process it may need to access the input device for say getting some value from the environment, or it may need to access the memory to get some operand if it is we are working with some variables doing some operation on them. And finally, whatever result is computed, if it is required that it should be flashed to the users, then they will be put onto the output device. So, this is the block diagram that represent the microprocessor based system. Now, if we look inside the microprocessor, in our architecture discussion, architecture portion of our lecture, so we have seen that any processor is made up of 3 main units. So, same is true for the microprocessors. So, the one of them is the ALU, arithmetic logic unit, another one is the control unit that controls the operation of all other parts of the microprocessor, and we have an array of registers for holding data while it is being manipulated. So, we have got this ALU, control unit and the registers. Now, these registers may be of different types that we will see slowly. So, if we expand the previous diagram a bit, then you will see that we have got a situation where this processor, so it is divided into ALU, register array and control. So, there is a system bus on which this processor is connected, this memory is connected, IO devices are connected. So, they are all connected over the system bus. So, you can assume that as if we have a bus. So, bus is nothing but a collection of wires, a set of parallel wires running in the chip. So, from this it may be on a board. So, if I consider this entire system as a PCB, so these are some copper lines running. So, from this copper line, so we have got these individual chips hanging. So, each of this processor, IO device, memory, so they may be a single chip or a collection of chips, and they are all connected to the system bus. So, they are hanging from the system bus. So, whenever this processor, so the system bus consists of say address lines, data lines and control lines coming out of the processor, and they are connected to the memory and IO in some as it is required. Okay. So, there are decoders and all that. So, they are not shown here, but at a block level. So, this is the situation. So, if we look into the memory in more detail, so memory stores information such as instructions and data in binary format, and it provides this information to the microprocessor whenever it is needed. So, it stores the instructions and data, they are stored in the memory. So, as I said that the processor, the microprocessor, when it is reset, it will be programmed to access a particular memory location. So, this programming is fixed by the designer of the microprocessor. So, there is a fixed address of the memory at which it will access, okay, and it is expected that the first valid instruction is there in that memory location. So, the processor will get that instruction, it will start executing it. So, if it needs data, it will again access the memory. So, in this type of design, in this type of memory organization, so what is happening is that we have got the same memory containing both program and data. So, program and data, so you cannot distinguish between them, like if by mistake I have a program in which I sort say 10 numbers, and this program is loaded from say memory location 1000 onwards, and the data set is there from location 1500 onwards. This 10 data set, they are stored from 1500 onwards, and the memory is the program is stored from 1000 onwards. Now, if by mistake the processor is told that the program is actually from 1500, where I have actually stored the numbers to be sorted. So, if I do like this, then it will try to interpret that data as instruction, and it will try to do execute that particular program, whatever be its meaning. So, that is the garbage, but the processor has got no other option. So, it will do that way only. So, in this type of organization, this type of processor organization, what is happening is that the processor cannot distinguish between the program part and the data part, and the program and data, they are part of the same memory. So, this type of organization where program and data are part of the same memory, so they are called von Neumann organization, where the program and data are put into the same memory. So, you can think about a better architecture, which are known as Harvard architecture, where this program part and the data part, they are kept in totally separate memory chips. So, program part will never mix with data part. As a result, the processor cannot do this mistake of taking a data as a program statement or program instruction. So, that type of architecture is known as Harvard architecture. So, the processors that are designed now, so they are mostly based on Harvard architecture because of this thing, but we can have both the types. So, both von Neumann and Harvard are there, but that is the basic difference. So, in a computer system, so memory is a subsystem. So, because subsystem means for the whole system, memory is a part of it, and memory is often a sizable amount of the system. So, it includes the registers, ROM and RAM. So, you see that it is a subsystem. So, it is a part of a system, but that system may not be a monolithic one. So, if you look into the components of the memory, so we said that it is registers. These registers are the CPU registers. So, they are actually residing in the CPU or the within the processor. On the other hand, this ROM and RAM, so they are typically outside the processor. So, we have got these registers, ROM and RAM. So, they are different parts, they may be distributed in the system in various places, but they are essentially part of the same memory, because the registers can also be made to store some value that way. So, this memory map, so this tells like how this memory is distributed for a particular design. So, for example, so suppose I have got a total address range for a processor from 0000 to FFFF. So, that is total 64K, that is the address space for the processor, and out of that, the from address 0000 to 3FFF up in this range, we have put one EEPROM. Okay. So, this is the there I can have some basic programs to be executed. So, that is kept in the EEPROM. Then 3FFF to 4400, so this part is not used. So, this address range is not used, but this RAM1 will be selected if the generated address is in the range of 4400 to 5FFF. So, that is the address range of the first RAM chip. So, this part, any address generated between these two, that is 4000 to 43FF. So, in that range, whatever address is generated, so there is no memory chip here. So, those are those should be detected by the operating system and told that there is no such valid chip there. So, they are address error or something like that. So, the RAM 1 is from 4400 to 5FFF, RAM 2 is from 6000 to 8FFF. So, that way we have got 4 RAM chips in this system. So, they are of different capacities and they are distributed over these address ranges. So, this is called the memory map of the system. So, if you are working with a system, a microprocessor based system, so you should know what is the address space, what is the address map, and of course, there are many other things that you need to know, but this is the first vital information. So, if you are trying to load your program onto this memory, you should not try to load it from address say 3FFF, or you should not try to load it you should not try to load it from 4000 onwards, because that space there is no chip, and similarly you should not try to load the program from F800 onwards, because in this range also there is no chip. So, rest of the places I have got RAM, and since we cannot change the content of EEPROM, we cannot write onto it until and unless it is accepting the programming part. So, you cannot update this EEPROM part. So, you should not try to write onto the EEPROM part. So, you should only read. So, once this memory map is known, so operating system can introduce those checks and it can introduce the error checks and all that. So, to execute a program, so the user will enter instructions in binary format into the memory. Apparently, it seems a bit awkward, like how the user will enter the program in a binary format. We never do that. So, we write our program in some high level language, and those high level language programs, so they are converted into this binary level, which is known as machine level, by using some compilers. But ultimately, as far as the execution of the program is concerned, so we have to load the program in binary format into the memory. So, that has to be done, and the typical system, so that is done by means of the operating system tools like loader and all that. So, that is a different part, different course in which you can learn about it, the system software utilities. So, once the program has been loaded into the memory, then the microprocessor will be able to read these instructions, and whatever data is needed from the memory, execute those instructions and place the results in memory, or it can produce the result on an output device. So, after executing the instruction, so the result that is produced is again another variable value. So, that value may be stored in some register, it may be stored in the memory, or there are some input and output instructions by which we can read the values from some input device, or we can write the values to some output device. So, in and out, so these instructions are there which can be utilized for that. So, there are 3 instruction execution model, 3 cycle, there are 3 cycles in which an instruction is executed. So, they are known as fetch, decode and execute. So, how an instruction will be executed? First, the instruction will be read from the memory. So, the microprocessor first reads the instruction, then it interprets it, and finally, it executes it. So, how to use this? So, we should give some proper name to these 3 operations. So, when it is reading the instruction, so this is known as the fetching of instruction. So, as if the processor is fetching the instruction from the memory. Once the instruction has been fetched, then the instruction has to be understood, like what does the instruction mean. So, that is called the decode stage, and after the decode stage has been done, then the processor knows like what is the operation to do, and in that case we have seen in our architecture lectures that there was a decoder, and the decoder generates a sequence of control signals to be activated, so that the operation is done by the functional modules that you have inside the processor. So, that way I can execute those instruction, the instruction gets executed by means of those activation of control signals in sequence. So, that is the execute phase. So, we have got fetch phase, we have got decode phase, we have got execute phase, and once, so after this what, like I have fetched one instruction, decoded it, executed it, then what? Then again the same thing, fetch the next instruction, decode it, execute it, then again the processor will fetch the next instruction, decode it, execute it, till it comes to a statement, an instruction which asks the processor to halt. Okay. So, normally all the processors, they have got one halt instruction. When this halt instruction is executed, then the processor will stop doing this fetch, decode, execute cycles anymore, and it will wait in that state until and unless an interrupt comes from the outside world, so that the processor is put back to its original mode of execution. So, that is the 3 cycle instruction model of any processor. So, this is very commonly known as fetch, decode, execute cycle. Okay. So, so even advanced processors, so they will follow this particular model. So, maybe in advanced processors this execute stage is very complex, that way it is divided into number of sub stages. This decode stage is complex, it is divided into number of sub stages, and fetch part, it is doing some sort of overlapping, in the sense that when you are executing the current instruction, at that time, so you can fetch the next instruction. So, that way there can be an overlap between this fetch, decode and execute cycles over the instructions. Okay. So, this is known as instruction pipelining through the processor. So, machine language. So, this is the language understood by the machine. Okay. So, like we are understanding English. So, when we are writing a program, so we are understanding the language C. So, when I am writing a program in C, so that is basically good for another person who knows the language C to understand what do I want to compute. But as I said that microprocessors or processors, so they will never understand this English like language statements. So, they will understand only zeros and ones. So, I should be able to express my program in terms of those zeros and ones. So, this is actually the machine language program. So, the number of bits that form the word of a microprocessor is fixed for a particular processor. So, that way it is so if it is fixed, so if I say that the word size is say 8 bit, so that will tell me what is the maximum number of combinations that I can have. So, if the word size is say 8 bit, then the total alternatives that I have is 2 power 8 equal to 256. So, the processor can use at most 256 different meaning of the word that is fetched from the memory. So, I can say that I can have 256 different instructions for this processor. If a processor has got 16 bit word, then I have got more flexibility in the instruction set design, where there can be 2 power 16 or 64k different types of instructions that are possible. But that is a huge number, and in most of the cases microprocessors will not use all these combinations. So, processor design even for an 8 bit word, so it may not be using all the 256 combinations. So, each of these patterns will be an instruction for the microprocessor, and the complete set of patterns will make up the microprocessor's machine language. So, this is the complete set of patterns that are possible. So, if a out of say 256, if a processor supports say 100 different instructions, so that information that there are 100 different instructions and which combinations mean what. For example, if there may be an addition operation, this addition operation is given a code. Okay. So, that what is the code? So, that is code means one particular 8 bit pattern. So, what is that pattern? So, that way if you note down all these 100 different patterns, so they are actually the machine language for the microprocessor.